Last time we had finished up talking about galvanic cells, and in a galvanic cell we place two half cells in close proximity, and the naturally spontaneous reaction takes place, and that causes electricity to flow. Now we're going to talk about something that's kind of different, and that's electrolysis. In electrolysis, we have a chemical system set up, and we run electricity through the system, and that's what causes the chemistry to take place. So that is what we have in electrochemical cells. We still have a cell reaction that is a combination of two half reactions, and it shows what's taking place. So let's start off with the example of molten sodium chloride. So we have heated sodium chloride solid up until it gets to its melting temperature. And once that happens, we have ions. So we have a sodium ion, and when we run electricity through, that gains an electron to make sodium metal solid. So sodium gains an electron, so it's reduced, and reduction takes place at the cathode. In an electrolytic cell, just like a galvanic cell, you have reduction at the cathode and oxidation at the anode. The difference is that in an electrolytic cell, the polarity changes. In a galvanic cell, the cathode is positive and the anode is negative. And in an electrolytic cell, the cathode is negative and the anode is positive. So we also have chloride ions in there, and two chloride ions will generate chlorine gas plus two electrons. So the chlorine is losing an electron, so it's oxidized and it's taking place at the anode. Now, when we have aqueous solutions, it's difficult to predict what will happen in an electrolytic cell, because you can have electrolysis of the water taking place, or you can have electrolysis of the dissolved ions taking place. In the example of potassium nitrate, which is something we commonly use as a salt bridge in galvanic cells, the water actually electrolyzes and the potassium ions and the nitrate ions don't. But in some other solutions, the dissolved salt ionizes. There's no way to know this just by looking, but if you look at a list of standard cell potentials, then you can figure it out. Or you can use information that's provided to infer what is going to happen. So let's look at what happens to water. If we try and electrolyze water, at the anode we have water, and it takes two waters. Two water liquid breaks down and produces oxygen gas plus 4 hydrogen ions, plus 4 electrons. This is what we saw when we worked with the little hydrogen cars. And at the cathode, we have a different reaction taking place. We have two water liquid plus 2 electrons produces 1 mole of hydrogen gas plus 2 moles of hydroxide ions. So we're breaking down this water as we electrolyze it. Now, if we look at this and we want to add these half reactions together, the top half reaction, the anode half, has 4 electrons, the bottom has only 2 electrons. So I have to multiply this by 2 so I can add them together. And when I do that, I get 2 waters from the top reaction plus 2 waters from the bottom reaction plus 2 electrons yields oxygen gas plus 4 hydrogen ions plus 4 electrons, plus 4 electrons here and 4 waters. I forgot to multiply. So we multiply this bottom one by 2, giving us 4 waters and 4 electrons. Then we get oxygen plus 4 hydrogen ions plus 4 electrons plus 2 hydrogen gas plus 4 hydroxides. And this is what happens when the hydrolysis of water takes place. So now if we look at this and we sort of combine things, we get 6 waters yields O2 gas plus 4 hydrogen ions plus 2 hydrogen gas plus 4 hydroxide ions. And as we learned in Chem 111, when we're looking at hydrogen and hydroxide ions on the same side of an equation, we add them together and they combine to make water. So I actually have 4 waters on the right-hand side. Now I can cancel 4 waters from each side, and what I'm left with for the overall reaction of the hydrolysis of water is 2 water yields 1 mole of oxygen gas plus 2 moles of hydrogen gas. And that's the electrolysis of water. And in this case, the cathode reduction is the formation of hydrogen gas, and that is preferential to reduce the water than it is to reduce the potassium ion. At the anode, I have the production of the hydrogen ions and the oxygen, and again, that's preferential to actually trying to electrolyze the nitrate. So in this case, we electrolyze the water. Now, sometimes we have the electrolysis of dissolved salts taking place, for example, copper bromide. In this case, the copper is reacting to grab 2 electrons and make copper solid, and the 2 bromides are combining to lose electrons and make bromine liquid plus 2 electrons. So our overall chemistry, when we subtract the 2 electrons from each side, is the copper 2 plus 2 bromides yields copper solid plus bromine. So how do we predict whether or not it'll be the water that undergoes electrolysis or the dissolved salt? Well, we can do this by looking at the reduction potentials in a chart, or we can think about it by comparing it to other data. So what would we expect to see in a solution of copper nitrate? Well, we already have information that says when the copper ion is dissolved, it will go ahead and get reduced. It will gain electrons. And we know that when the nitrate is dissolved, we actually have water undergoing electrolysis. So water gets oxidized at the anode. So what this would tell us is that at the cathode, we'd have our reduction. We'd have copper 2 plus 2 electrons, making copper solid. And at the anode, we'd actually have the water undergoing electrolysis. So the 2 water liquid would be making O2 gas plus 4 electrons plus 4 hydrogen ions. So to add these together, we need to multiply the copper by 2, since I only have 2 electrons in that half. So when we do that and add these together, we get 2 copper 2 plus 4 electrons plus 2 waters yields 2 copper solid plus oxygen gas plus 4 electrons plus 4 hydrogen ions. And our electrons cancel from both sides. So what we're left with is copper 2 plus water yields copper solid plus oxygen and hydrogen ions. So in one case, we have electrolysis of water taking place at one electrode and the electrolysis of the copper ions taking place at the other. Now let's look at potassium bromide. Previously, when we had potassium in solution, we had the water undergoing reduction at the cathode, and the bromide was oxidized at the anode, so that's what's going to happen here. So at the anode reaction, we have water. 2 waters plus 2 electrons yields hydrogen gas plus 2 hydroxides. And at the anode, where we have the bromide getting oxidized, we have 2 bromides yields bromine, which is diatomic, plus 2 electrons. I don't need to do any multiplication. I can just add these together because the 2 electrons cancel out from each side. So I get 2 water plus 2 bromide yields bromine plus hydrogen plus 2 hydroxides. Now, when you look at these and think about what would I expect you to be able to do on the test, I'd expect that if you were given information about electrolysis of a potassium nitrate solution and then a copper bromide or some similar information, that you'd be able to make these same understanding and come to the same conclusion that this is what would happen. So I'm going to stop here and start the next video.